Okay, we are on 2 degree of freedom systems, and we will be talking about the coordinate coupling. That is how the coordinates are related to each other in the system equations. First of all, we know that if a system has n degrees of freedom, you require n independent coordinates to describe the motion. That is to write the differential equations. But if you have a simple system like this one, in which you have like the one at the bottom that has two masses, it's pretty straightforward. You have x1 and x2 as coordinates. That's no problem. But in some systems, the coordinates might be different coordinates might be used to describe the same system. For example, consider a lake like this one, in which there is the center of gravity is located at a distance of L1 from one side, L2 from other side, and it's on elastic foundations, so that you have springs on both sides. Now, you would like to model the motion of this lake, let's say. This is a 2 degree of freedom system. If you want to write the equations, you have multiple choices. For example, you might choose the displacement of the center of gravity x and the rotational angle theta as a set of coordinates. You have two coordinates like this. Or you might use y and theta, y being a rather arbitrary point, let's say a distance of e from the center of gravity. Or you might choose x1 and x2, which are the displacements of the springs. Or you might choose x1 and theta. Let's say you might choose x1, this one, plus the rotation theta. They all are still valid coordinates, okay, all of them. The system has 2 degrees of freedom, but the equations you write for each of these equations will be different. Let's see how they will be different. First of all, the equations you will be writing with all these coordinates are going to be coupled. That is, let's say x coordinate and theta coordinate will cross terms in the equations. X equation will contain theta terms, and theta equation will contain x terms, and so on. But you will have mass and spring matrices, as you know. If the stiffness matrices has coupling terms in it, cross terms in it, it is called a statically coupled system. If, on the other hand, if the mass matrix has coupling terms in it, you call it dynamically coupled or inertially coupled. If the system has both the stiffness and the mass matrix cross terms in it, you call it, well, both statically and dynamically coupled. We will see that the coupling is affected by the choice of the coordinates. Different choices will give you, different coordinate choices will give you different kinds of couplings. For example, again, we take our late example. If you work on it, actually, I would advise you to work on that. If you use x and theta equations like this one, you will see that the mass matrix will be uncoupled. There are no cross terms in the mass matrix, but there is a stiffness term in the, coupling term in the stiffness matrix, like this one, minus K1L1 minus K2L2. As you see, they are both the same. As you know, mass and stiffness matrices are symmetric. So x and theta equations are statically coupled. Okay, here you have static coupling. On the other hand, if you use y and theta, and y we said is a distance of e from the center of gravity, this is the distance y. If you write the equations like this, you will get, in your mass equations, you will get an ME term. So you have dynamic coupling here, dynamic coupling. And also you will have static coupling as well, because you will have cross terms here. But if you select this E value such that K1L1 prime is equal to K2L2 prime, these terms are going to drop and you will have no static coupling. So if K1L1 prime and K2L2 prime are equal, and you can select E so that they are equal, in that case, your system is not going to have static coupling. So different coordinates have different kinds of coupling. So we reached an interesting conclusion. Coupling of the mass and stiffness matrices is not a property of the system. That is, the system does not have coupling, but the equations do. That is, the coordinates. If you select the necessary coordinates, the equations might be coupled, or they might be uncoupled. It is possible to uncouple them. That is the idea here. So the question we have is the following. Let's say that we have a system that has static or dynamic coupling, such as this one, let's say, okay? This has static coupling, actually. The masses are uncoupled. Well, if you use x1 and x2, can we find the coordinate systems somehow, instead of x1 and x2, can we find a coordinate system, let's say q1 and q2, such that the equations are uncoupled? And that is the problem in the modal analysis. And the answer is yes. That is, if you find a coordinate system in which the equations for the system will be uncoupled, like here you will have mq double dot, let's say, not m plus, let's say, kq equals 0, q1. And let's say that these are bars, and let's say this is m hat q2 double dot plus k2 hat q is equal to 0. As you see, q1 and q2 have no relation to each other. In this case, these equations are very easily solvable, so they are uncoupled equations. And the coordinates which you use here, the q coordinates, are called the modal coordinates. So, in principle, we should be able to convert the physical equations by a coordinate transformation, which we will call x equals pq, or the q equals, let's say, p inverse x, as we will see. This coordinate transformation converts the x physical coordinates to q modal coordinates. It's possible to do that in the vibrations, and that is the main idea of modal analysis. You want to convert the equations to modal coordinates. Let's give you an example. Let's say that we have this classic system in which springs are the same, masses are the same. You have physical systems, physical coordinates x1 and x2. We want to convert it to our model system by a coordinate transformation. We know we have solved this problem before. These are the natural frequencies, and these are the mode shapes of the system, 1, 1, and 1, minus 1. And the physical solution to initial conditions, to IC, let's say, is, as you know, it is a combination of the first natural frequency and the second natural frequency, first mode and the second mode, with first and second natural frequencies. Now, if you did a modal solution to this system, actually, if you solve this modal system, you would be obtaining something like the first mode of the system will give you a response in the first natural frequency. The second mode would give you a response in the second natural frequency. Actually, in this case, you should be able to obtain, if you use P is equal to U1 and U2, that is the mode shapes, the transformation matrix, if you use the P matrix as the combination of the mode shapes of the system, X can be converted, the physical coordinates X can be obtained from the modal solutions, okay? So as you see, for example, x1 and x2 can be solved from, if you can solve the modal equations, x1 and x2 can be obtained from x equals pq equation, which is a back transformation. So the idea is the following in the modal analysis. You have to transform to modal coordinates in which the system is uncoupled. Okay, modal coordinates are uncoupled, and uncoupled equations are easy to solve. Okay, you have to convert the initial conditions too, by the way. Then the problem is easy to solve in the modal coordinates. So solve the problem in the uncoupled modal coordinates, and then once you get the solution, you have the transformation. So you transform back to the physical coordinates. We will use this idea quite a bit during the upcoming lectures in the course. Okay, so much for the coupling. There is one more thing I want to talk about in this video, and that is the semi-definite systems. There are certain systems which are free to move. That is, they are not connected to the ground by a spring or a damper or anything. For example, let's consider these two masses, M1 and M2, connected by a spring, something like a locomotive and a wagon, let's say, pulled by it. And this thing is free to move in one direction. That is, it can go along in this direction. It also has vibrations, but it can act like a single mass with vibrations. But how do we analyze this? We can write the equation of motion for this system. As we see, we get the following mass and stiffness matrices. But let's assume that you have a harmonic solution. If you assume that there is a harmonic solution, we get a characteristic equation from determinant of, comes from determinant of k minus omega squared m equals 0, gives you the following equation, okay? From which you can solve for the natural frequencies, and the first natural frequency comes out to be a 0, okay? And the second natural frequency is something, it doesn't matter. But this means that the system does not vibrate. This means no vibration. This means rigid body motion. The system makes rigid body motion, and the corresponding mode shape actually here will be 1, 1, okay, as you find it. Now, there are certain systems which are free to move like this, they are not connected to the ground or fixed to the ground by a spring or a damper. Such systems that have rigid body modes, this is a rigid body mode, by the way. If they have rigid body mode, one of the frequencies is 0, natural frequencies. And for these systems, the determinant of the stiffness matrix is 0. And the natural frequency corresponding to that is 0. In that case, in that mode, the system is going to act as if it were a single mass moving like this, making rigid body motion. Another example of this is, for example, a turbine blades connected with a shaft. In both ends, it's not connected to anything, so that this system is also a semi-definite system. It doesn't have, well, it has a rigid body mode, which means it will be purely rotating like without any vibrations, and that will be its rigid body mode.